Hi, my name is Mingil Lee from Group 100. We are going to have a brief explanation of each part of the code. This is tiny 16 by 16-bit RAM that handles 16 addresses and 16-bit words. The RAM consists of clock, clear, RI, and RO, representing write enable and output enable. We predefine the instruction in the RAM according to control logic opcode. The constant on the left side in red representing addresses, and the right side indicating its instruction from address 0 to 8, and the data from 14, address 14 to 15. This module is a 4-bit program counter. It increases every clock when enabled, can jump to a new address from the bus, and outputs its value to system bus only when CO equal to 1. It's how the CPU knows which construction to fetch next. And the next one, this is a memory address register. When MI equal to 1, it takes the lower 4 bits of the system bus and stores them as the address for RAM. The next one, this is a register. It stores 16-bit data from the system bus when AI equal to 1, and outputs its data to the bus when AO equal to 1. It also sends its value to the ALU for calculations. The next one, this module is the instruction register, or IR. It holds the 8-bit instruction that the CPU just fetched from memory. The upper 4 bits are opcode, which tells the CPU what operation to perform, and lower 4 bits are operand, which tells it what data or address to use. When I is 1, the instruction is loaded from the system bus, and when IO is 1, it can place the instruction back onto the bus. Then control unit reads the opcode and operand to decide the CPU's next action. And the next one is the arithmetic logic unit. It does 16-bit addition and subtraction. The next one is this is a control unit. A control unit is CPU's brain. It runs every instruction through 5 micro steps: fetch, decode, memory access, and execute, which is here. At each step, it turns on control lines like MAR in, RAM out, A in, or AAU enable. So the write data moves through the CPU. The opcode decides which path to take. For example, the LDA reads from memory, ADD and SUB use the ALU, and JMP loads a new program counter. After execution, it resets to fetch the next instruction, creating a smooth, continuous CPU cycle. Next one. This is my top-level 16-bit CPU. All parts shares a single 16-bit system bus, controlled by the control logic. the program counter sends the address to memory address register, and the RAM transfers data through the bus. Instruction register stores the fetched instruction, while A and B register feeds the ALU for arithmetic operation. The ALU's result goes back to A or to the output register. The control logic reads the OP code and coordinates every fetch, decode, execute, and halt step automatically. The next one is this is my top level view. This is a program counter, and the program counter sends the address to memory address register, and memory, and then where is it? And then from RAM, the IR instruction register, the receive instruction from RAM, which is fetch cycle. Then this control logic is here. Control logic decodes the instruction in IR, and once the instruction the data in IR is instruction, the address sends to MAR, and then received the content at the address, and then send it to the A register here. If the second instruction from the memory is add, the control unit decoded and direct to calculate in ALU. Once it is calculated, the data is sent back to register A, accumulator register, and the data is sent back to the RAM again after that. And this one is predefined instruction here. The test result demonstrates that the regular clock signal influences the performance of other components. The program counter operates on the rising edge of the clock signal here. During the fetch stage, the memory address register receives the address from the program counter here. And the predefined instructions stores in the RAM are successfully loaded into instruction register here. However, the decoding process appears to be improperly implemented. The total sum should have been displayed the value of A in the second cycle, but since first instruction LDAE should have been stored in the accumulator register and subsequently added to the value of 3 during the next cycle, we assume that issue is caused by micro-step signal. Step 010 represents decoding process which does not respond to clock signal.